121.1.
Over to tower, we stand boxes.
The AGM at 2503 heavy, contact tower 120.905.
Live, we are live. Hello, welcome to week 3. People are still trickling in here. I guess people had a hard weekend, tough weekend. So hopefully everyone can hear me online. And if you can, positive confirmation would be good in the thread window. If that's the case, whoever's online. And of course, people can always pick up later and just rewind. So if you're playing catch up. I think there's an outlet behind the Tesla battery on the wall there. Is there? So here's some more people. All right. Good, good. Welcome.
We're back.
Welcome. Is there only?
The sound was really good last week, though.
Okay, great.
Yeah.
Awesome. Yeah, I don't know if there's any outlets over there. You might have to swing up here.
I'll have the beer in the kitchen.
Oh, okay.
Mine in the fridge.
Marcy told me to sit down.
So the AC unit, yeah, sure, because we're not going to use that. I didn't even know that was plugged in.
I don't think it's coarsely long enough for that. Yeah.
All right, there we go. Well, all right, a little tardy, but I'll just take a couple points off your quiz. That's all.
I was like, quiz. Knock me down.
No, not a quiz.
Thank God.
I appreciate that you were as late as you were, because otherwise we would have. As long as you're not the last one in, you're not late. Carrying that beer and slowing me down.
Marcy might join us today. I don't know.
She said she was going to. She said
Yeah.
going to drag the tables.
All right, groovy. So I'm going to start with a recap. There's my doodad. Start with a recap. Yes.
So
All right.
my question that I posed.
Yeah. Did I answer it or?
Well, yes, but Doug Russell clarified, not like stall as far as like climb stall, but minimum speed to have lift. Right?
Say that again.
Because it was, unloaded was.
Well, it's load factor. So it's not meant to be the weight of the aircraft. It's meant to be the excess weight. So the excess load it infringes on your excess lift because the plane is designed for that margin, right? So as the load is increased, you're decreasing that margin, which is, you have to have a greater angle of attack in order to create enough lift to come over that load factor.
Right.
That's what brings that speed up. Because your margin is reduced. So your critical angle of attack is the same no matter what. You just need to have a higher bite of air as you're flying to carry that load, right? So that means your margin between your critical angle of attack and stalling is narrower, and it's at a higher speed because of that. You've lost that margin.
Right.
So that's why. So it's not like weight.
Right.
That's different. Yeah.
I was thinking, but
I mean, weight too. You'll need a steeper angle of attack, to carry that load too, the weight. But we're talking specifically about load factor in that statement. Yeah. Yeah, I think everyone wanted more time with angle of attack and stalling and stuff. Zach was just asking about that. I have a lot of material to cover today, so I don't know if I can do it in this class, but maybe what I'll do is I'll set up a special Q&A session if that works with you guys. I'll just schedule something sometime this week that works, and then we can just set aside an hour and just talk about it. Is that cool with you guys? Yeah? Okay. All right, so material. Here we are. So I asked you to read chapter 7 and 8. Chapter 7 was pretty long. But if you're into cars and engines and stuff, it should have been an easier read than some of the other stuff. So hopefully some of you are able to get through that. Then chapter 8 was all about the instruments, the static system, the pitot system, the gyroscopes. And all that might be extremely new to you. So We have a lot of information to cover in both of those chapters. So if I'm going too fast, just either say something in the Slack window or raise your hand or fart or something. I don't know. Whatever. So I'm going to go quickly recapping. So we talked about angle of attack, and that key there is the chord line and the relative wind. That's your angle of attack. So here's a cross section of the airfoil. Chord line goes from the trailing edge to the leading edge, and then that camber upper surface is usually longer. That's what causes a lower pressure, which draws the wing up. The angle of attack in this case is the important thing to know is the chord line here. So angle of attack is the relative wind versus the chord line. So it's the angle between the chord line and relative wind, and it applies to all airfoils on the aircraft. And then there's a airspeed on each angle of attack to maintain altitude in an unaccelerated flight. So you're balancing the force of lift and weight, and depending, which way you're going, drag and stuff. Good question, Brian. I don't know. You're gonna have to tell me, I guess. So. Never mind. I'll just write a question. Good. As thrust is reduced and airspeed decreases, the angle of attack must be increased in order to maintain altitude to balance lift and weight. So if weight is increased, then angle of attack, right, must be increased to increase the lift to overcome the weight to maintain altitude in steady unaccelerated flight. The critical angle of attack, this might be on the quiz. The critical angle of attack does not depend on weight or airspeed. And lift is decreasing rapidly at the critical angle of attack, and then the plane will stall. So big thing, just remember angle of attack, chord line, relative wind, any airspeed. It's a design. Critical angle of attack also is a design speed. It depends on the design of the wing. Yeah. Each aircraft has an angle of attack where airflow separates from the upper surface of the wing and the stall occurs. That's you may say that's boundary flow, where the air starts getting turbulent and is no longer creating that nice sucking action on the top of the wing. And it's usually between 16 and 20 degrees depending on the aircraft's design. Again, on the design of the wing, not the weight, not the airspeed, not the density of the air, the design of the wing. Ground effect, we talked a lot about, there's a lot of questions. If you looked at study unit 1, did it have the ground effect ones? But, or study unit 2, well, and after this class, you'll be able to look at study unit 2, you'll have enough information. But, the plane may appear to fly before it's actually achieved a recommended takeoff speed because your induced drag is reduced, so you don't need as much lift and thrust to get off the ground. You get off the ground, once you leave ground effect, that induced drag comes in, and you don't actually have enough lift to leave ground effect. So that's why it can be dangerous. So in this case, the aircraft might settle back down to the runway, and then what are you going to do? Just forget it or try again? A lot of people try again, and they don't make it. So the other thing is that a landing can be delayed. As you settle into ground effect, the plane just doesn't want to come down. We talked about balancing what the tail's function is in the aircraft, and why it's there is really to balance the aircraft during against the center of gravity and the coefficient of lift. And we also talked about if the CG is in a position where the tail can't overcome that, it's impossible to recover from a stall. Can get into situations where you can get into a flat spin. We talked about that, where the center of gravity is actually pulling you deeper into the spin, and it's harder and harder to get out of it.
So when you're setting your trim, is that affecting your elevator?
It does. It affects the elevator. It's mainly to help you as the pilot not to have to keep and maintain that force. So if you're in a climb, you might trim the tail out in the climb to balance your loads out, so you don't have to hold back on the yoke. So you'll be pulling on it, and then a climb can take 10 minutes depending on the conditions and the rate of climb the aircraft is. And you certainly don't want to be sitting there for 10 minutes just holding it back, so you can trim it out. Okay. Yeah. And a side point too, there's a trim configuration for takeoff that they recommend. There's a little white marking on the trim wheel that indicates where the trim should be during takeoff. That way you're not doing something where you've trimmed it nose high and then all of a sudden you get in ground effect and you're and yeah, very bad. Don't want to do that. They use the downwash over the wing and the tail as a combination to help produce some aspects of stability and basically restore the plane to an attitude which is a stable attitude. So if you aggressively move the nose up, it wants to push down, and if you aggressively push down, it wants to nose up. It wants to fly, right? So part of the function of the tail does that as well. We talked about forces in a turn. Yes, yawing is pushing on the rudder pedals, moving the rudder, and it will point the plane, but it really doesn't create a turn. In order to create a turn, what you need to do is you need to redirect the component of lift to the inside of the turn that you want to go, and the way you do that is you bank the wings with the yoke or the stick to either direction you want to go. So what that does is that shifts the component of lift to the inside of the turn and then pulls you into the turn. Once you're established in the turn, you need additional lift because you're stealing that lift that was just keeping you in steady altitude. You're stealing that lift for the turn. So to have the same amount of lift to keep you at altitude, you're going to have to increase it somehow. So you can add speed or you can increase the angle of attack to increase the lift. Bless you. And we also require additional lift because of the centrifugal force, and this is loads, right? So centrifugal force and weight combined into a resultant load. So the lift has to come over the load. It also needs to make up for the fact that you've taken that lift vector and redirected it to the inside of the turn. So
You've got a question.
I do. Let's see if enough thrust in your. Got it. Move it over. Let's see. Enough thrust with the aircraft, you could fly at some crazy angle. Yeah. So remember the functions for lift includes a velocity, right? So, but it also includes a drag function, right? So you're going to have to be at a point where you're going so fast, you're still not overcoming, or you have to be able to overcome lift and overcome drag. Lift and drag both increase as you increase airspeed, and then there's a point where you can't overcome lift anymore. So yes, you could increase the airspeed, but then again, we're doing this load factor thing where you're decreasing your margin of safety. Your excess lift is reduced, your excess load is reduced, and that margin of safety becomes narrower. So I hope that that answers that question. As long as you remain within the design limitations of the wing, yeah. So as long as your load factor, if you remember that VG graph, right? That's really what it comes down to. As long as you're within the green or yellow area with non-turbulent air, then yeah, you can use speed to increase lift. Then your radius of turn increases, and then you remember the big diagram of the guy in the box canyon that was trying to get out of it. And he didn't climb, he just stayed at the same altitude. So, yeah.
We don't know. One diagram that appears as though he might.
So one diagram appears as if he did go down. I think it looked like he just slammed into the edge of the canyon, but yeah. So when we do increase, when we do change the lift factor to the inside to make the turn, what happens is that, yes, we get more lift on one wing and less lift on the other wing, which causes that wing to raise and the other one to lower, but we also increase the drag and reduce the drag on the other, and that causes this thing called adverse yaw. So basically the nose will want to point in the direction of the raised wing, and to overcome that, we need to apply rudder pressure on that outside of the turn. Also, an airplane will naturally slip. So if you don't apply rudder pressure, it will slip if you make a turn without using the rudder. And they say that because there's tons of questions about, is this a skidding turn or a slipping turn, or which side of the ball and the wings, when we talk about turn coordinators, is a slip and which one's a skid. But if you just remember, if I bank the plane and I don't do anything with the rudder, I'm slipping. If I aggressively push on the rudder in that turn, I'm skidding. Yeah. Yes, question.
Will we go more in depth on that later?
Well, the flying handbook talks a lot about it, but we'll talk a little bit about this in the, I mean, it's really a practical flying thing, so here it's kind of like, just know that these are the conditions that happen. So practically flying, you'll definitely experience it. You know, you'll be in the plane and you'll turn, and then it's just kind of like doing that. You need to apply that rudder pedal to bring that plane in the inside. I said rudder on the same side as the raised wing, and that's incorrect. It's on the inside of the turn. So, but yeah, we talk about turn coordinator, and that has the inclinometer in it, which indicates if you're slipping or skidding. So when you think about if you banked and the thing's shooting out, and what rudder pedal you need to press to correct it, you can easily understand which is a slip and which is a skid if you think about it that way. So banking the plane and not applying rudder pressure on the inside of the turn will cause a slip. So you would see an inclinometer showing a plane banked left with the ball on the inside of the turn, because it wants you to push on the rudder pedal there to bring the turn around. We also talked about effects of propellers. So we talked about torque reaction, slipstream, the corkscrew effect, where the air going over the aircraft is actually hitting surfaces and causing it to turn because of that. The gyroscopic action, where I took the gyroscope, spun it, and then tipped it up, and it went off to the side. Asymmetric loading, there's questions on the written about that. Propeller takes a bigger bite of air on the downstroke. So these, all four of these, I think, are covered in the written test, so expect to see them. I also mentioned that multi-engine planes are funky because of that center of thrust line in them. We all need to know weight and balance. We'll actually be going on an entire chapter section on that later. Okay, so now the new topic. 17 minutes in and the new topic. So this chapter was all about aircraft systems, right? So the engines, the induction system, the electrical system, just everything in the aircraft that has not to do necessarily with navigation or necessarily flying the plane, but has to do with the operation of the aircraft and the fuel. So when we talk about these planes, we're talking about 4-cycle combustion engine. I know the book went into 2-stroke engines, but that's not the case with the typical planes we'll fly. So I'm only going to be focusing on the type of stuff we fly. That's why I said don't bother reading the turbine, turboprop stuff, turbocharger stuff. This engine design is practically unchanged for 60 years, if you can believe that. They started out with radials, then they had tried V, and then what they found out is that this horizontally opposed engine is the one that worked most efficiently for cooling the engine. So that's kind of the way it's been in most planes. They're horizontally opposed. You'll still see radial engines and sometimes you'll see V engines, but for the most part, horizontally opposed, and it's usually 4 or 6 cylinders. The spark plugs are driven by a dual magneto. It's independent from the electrical system, which is great because if you lose electrical, the engine continues to run. You can also start the engine without the electrical system. You can hand prop the engine, but not recommended unless somebody behind the controls knows what they're doing. Otherwise, you're going to lose your hand or your head or something. So, fuel systems are typically a carbureted or fuel injection. More commonly now, fuel injection. You get into older airplanes, they'll have a carburetor. We'll talk about carburetor icing, which can affect the power delivery of the engine. The cooling system, typical stuff, right? Air circulating over the engine, huge in airplanes, probably not as much in cars. Oil, both important in cars and airplanes. But yeah, cooling, huge aspect of keeping the engine running well when you're flying. So the components of the aircraft, and we'll be talking about is not necessarily yoking that, but in the first part of this, I'm going to talk about the throttle, the propeller, which is the blue handle, and the mixture, which is the red handle. So start with the engine, right? 4-stroke, 4 cycles. So this way they will ask you about the 4 cycles of the engine in the written test. So the throttle is controlling, I'll just say, the timing of the valves in the spark is mechanical. I think that's pretty much the case in cars too, right? It's either connected to a timing belt or something mechanically connects it to the actual crankshaft, so everything times up. And if you've had timing problems in your car, you'll hear that's it's not sparking right, or it's it's just jerking around. And the airplane, it's mechanically connected too, but not usually with a belt, but usually actually a geared connection, so it's a little more robust. The throttle is what's going to control that amount of fuel-air mixture going into the combustion chamber. Specifically, that's how they word it. You'll see it on the test like that. So the amount of fuel-air mixture, you have control over the fuel-to-air ratio. The throttle, the black control, is the amount of that mixture that's going into the combustion chamber. So an open throttle is you push the control up or you raise the lever on a lever. It's going to open the throttle. It's going to put more fuel air into the engine. And closing the throttle, pulling back, it's going to be less fuel air mixture going into the engine. When you cut the engines, when you stop the plane, you'll pull it full close and you'll lean the mixture all the way out. So the four cycles are intake. The intake valve opens, the piston draws in that mixture of fuel and air. On the next cycle, the piston moves up and compresses that mixture to get a bigger impact when it explodes it on the power cycle. This power stroke, that mixture is ignited, drives the piston away, and it delivers that to the crankshaft, which is connected to the propeller. Then on the last stroke is the exhaust, the combusted mixture is pushed out, the exhaust valve, and we start all over. And the cylinders aren't all doing this at the same time. They're all doing it at different intervals. So one cylinder might be on 1, another one on 2, another one on 3. I mean, how it works out. But that way, there's always continuous power being delivered to the engine, and also balances the engine by doing that.
Now, can we get back to that one?
Sure. Water.
Okay.
Groovy. The prop control, the little blue control, you'll see it if you have a constant speed propeller. You will not see it if you have a fixed pitch propeller. In the fixed pitch propeller, the throttle is adjusting the RPM. The propeller is specifically right there on the shaft with the engine. Can't do anything about it. And that's reflected in the tachometer in the airside. So you won't see a manifold pressure gauge in a fixed pitch propeller instrument bay. You'll just see a tachometer. And that's a direct reflection of the power being, or the amount of energy being delivered by the engine. So that's controlled by the throttle alone. So you'll see that in Cessna 172, the Diamond 20, the DA-20, and like the Archer or the Cherokee Warrior, the Piper line of aircraft. Constant speed propeller, on the other hand, the throttle adjustment is adjusting the manifold pressure. It's reflected in the manifold pressure gauge, and it's in inches of mercury. If the engine is shut down and you're sitting on the ramp, it will actually indicate static air pressure, whatever the barometric pressure is. You'll see on that gauge. What you do with the RPMs is you can use the propeller control to set the RPM. And what this allows you to do is come up with combinations of engine horsepower or engine power and propeller speed that it's sort of, I mean, the best way to think about it is like a gearing system in a car, right? You're going to go up a steep hill, you put it in low gear. You'll get the maximum power out of the vehicle. So for example, when you're taking off, you'll put the RPM, the propeller control full forward, because you want it to have the least amount of bite of air, and you want it to spin the fastest for all that power that you're sending to it. So in takeoff, the blue one will be forward and the throttle will be full forward, and you scoot down the runway. Where adjustments come in handy is when you're in cruise and now you're just zooming along and you want to make the engine perform more efficiently, use less fuel. There's combinations published in the handbook that say, okay, run the manifold pressure at 20 inches and then run the propeller at 18, for example. And then lean it out with the mixture, and you'll end up burning 14 gallons an hour. But if you were just having it full bore the whole time, you burn like 28 gallons an hour or something like that. So you have a lot more control over how much power is being delivered and how much stress there is on the engine at the point by manipulating it. Typically, max power, like I said, can be delivered with the highest allowable RPM and high manifold pressure settings. One important thing, and I'm not sure if this appears on the written, but you never want to have the prop low, like taking big bites of air with a lot of power coming out of the engine, because that's just too much stress on the crankshaft. So it's like putting it in fourth gear and trying to start from stop, I guess, is the best way to make an analogy there. Mention the mixture control briefly. So I said the throttle controls the amount of fuel-air mixture delivered to the engine, right? So the fuel-air ratio is its weight of each fuel and air. It's weight of air and fuel. It's not the volume, it's the weight entering the cylinder. That's important, and there's questions on the test that will try to trick you on that. So air density affects power output. So as the air thins or thickens, the weight of fuel in the mixture remains unchanged, right? So if it's weight of fuel and weight of air, if the density of air is changing, you know, that means that there's going to be more fuel present as the air thins, or there'll be less fuel present in that ratio as the air thickens. So this is causing that mixture ratio to change. So during a climb, that mixture becomes richer. There's relatively more fuel in that mixture because the density of air is decreased. And then during a descent, the fuel-air mixture becomes leaner. So there's relatively less fuel in that mixture. And if you've leaned the airplane for high altitude flying or flying from a high airport and you don't enrich in it coming out of it, the engine could quit on you as you're coming into your lower altitude airport. So they talk about it the other way around, but nobody really thinks about it going in. So if you never pay attention, the other thing that can happen is your engine can overheat running too lean like that. So typically though, either way, you'll see a loss in RPM or a manifold pressure in a RPM in a fixed pitch, manifold pressure in a variable speed propeller. And I said that high altitude, lower density, the mixture must be lean to keep the ratio balanced. At high altitude airports, this may be needed to eliminate roughness. So if you don't adjust it and you got everything full up and you're taxiing around and the engine's like, it's getting flooded basically, or the spark plugs can get fouled. So there's fuel that's actually not burning and it's collecting on the spark plugs. And then that creates a carbon deposit. And then what can actually happen is fuel can actually detonate on that deposit because it's hot before it actually gets sparked. And they talk about that as one of the behavior, detonation and pre-ignition they talk about in the written. So mixture control is that red dial or lever, and it lets you change this ratio. So you push it to make it richer, you pull it to make it leaner. When you shut the plane down, you pull the throttle and the mixture all the way back, it'll cut the engine. Leaning the mixture will decrease the fuel flow, which compensates for the decreased air density at high altitude. So the higher you fly, you can burn less fuel, right? But it's going to take a lot of fuel to get up higher. So it's like one of these games. So if you're taking a short flight, that probably doesn't make sense to climb high, but if you're flying for 2-3 hours, it might go up a little bit higher. You can bring the fuel back, burn less fuel overall. So there's things that you think about when you're flight planning too. Especially if you own a plane. If you're paying a fixed price and you don't care because they're covering your fuel costs, you probably won't pay attention. But incorrect use of the mixture can cut the engine, obviously. It can cause overheating. It can cause abnormal engine operation. And it can cause unexpected fuel burn or shorten the endurance of your flight. You plan for the flight, you never leaned it back. You think you got 30 minutes more of fuel when you get to your destination, but oh, shit, I never leaned the plane during the flight, and now I've actually burned through all that reserve that I thought I had. So it's an important function, and understand why, what effects it has. The induction system, so this is the carburetor, the fuel injector, is responsible for mixing the fuel with the outside air. An air filter is there to prevent debris from entering this mixture, and if the air filter gets blocked by ice or bird nests or I don't know, whatever, you're not getting anything to go in there. So you'll know in flight if your air filter or your air intake's been blocked by ice or snow, because you'll see a reduction in power, right? There is an alternate air switch in most planes, and some of them are automatic. On the Cessna, there's an automatic one. If the air intake gets clogged up, the automatic one will just take over. In our plane, we actually have a lever that you pull down to open alternate air, and it comes from inside the cabin. So that means it's a little bit warmer than the outside air, so the density is a little bit less. So you have to take that into consideration. You'll see, if you just operate the alternate air, like if you're just doing a run up in the plane, you operate it, you'll see a reduction in power, from using the alternate air, even, outside, from the outside air. As I mentioned, there's two types. There's a carburetor. The most common is this float type carburetor. And this operates on the principle of a pressure differential and a venturi throw to the carburetor. And that's what that airflow through there is actually controlling how much fuel gets pulled in and mixed in. It's really an interesting thing. I'm not going to get too deep into it because we got so much to cover. But you saw the diagram in the book. I have it here too. It's pretty clever when you look at it. Like, they had come up with this idea before a fuel injection system. It's just a mechanical way of mixing fuel. It's pretty smart. What's that?
I said, now I understand where it fits in.
Oh, okay. You understand where it fits in now, yeah.
The other chapter did not. I'm going to explain it, but not.
So there's mainly older planes, and smaller planes will have a carburetor type system. It's not as expensive as a fuel injection system. The fuel injection, air and fuel are regulated as they're injected in each cylinder, well, nearly there. Here's that picture from the diagram. You see this little venturi throat thingy doodad here. I don't know if I have a pointer. Do I have a pointer? Oh, snap. Okay. So this right here, this little teepee thing or pyramid thing here is bringing the fuel in. And then the fuel mixture valve here is controlling and regulating how much airflow is coming through. And then the venturi throat is actually, that lower pressure is what's drawing the fuel in. So by controlling that, you're controlling the ratio. Like I said, it's pretty fascinating, but beyond what we can cover here today. The fuel injection system, more common nowadays than it used to be, incorporates these 6 components. Right? There's an engine-driven fuel pump, the fuel air control unit, a manifold, which is the distributor, the fuel distributor. These nozzles that are actually discharging the fuel into each of the cylinders. Then there's an auxiliary pump in a lot of planes in case the engine-driven one fails for whatever reason. You have a backup electric-powered auxiliary pump. And then, of course, the indicators that are showing you what's going in and out. So you could argue that this looks less or more complicated than this looks less or more complicated. Obviously, there's more parts here. This is definitely a more expensive system to maintain, but more reliable. And it's not as subject to icing, we'll talk about next. So carburetor icing is because of that venturi, that narrowed throat. So as you reduce the pressure there, you've actually reduced the freezing, or raised the freezing point in that throat. So you can actually get icing even if it's like between 20 and 70 Fahrenheit. And I meant to put Celsius in here for our international friends, but I don't have it, sorry. Marcy might know, she memorizes that conversion. Anyhow, so you have to have a humidity. So even at 70 degrees, you can get carburetor ice. So typically, when you're doing pattern work in an aircraft, you'll pull the carb heat. No matter what the conditions are, it's just a habit. You'll do it once you reduce that engine power. So a drop in RPM on a fixed pitch prop will be seen if the carburetor ice is formed. That's how you know that you're not getting a good mixture anymore, because that ice is in there, preventing the mixture from being correct, what it should be. So planes here have a carburetor heat. It's just like a little thing you pull out right there. It's a pull push type thing. Like I said, older 172s, 150, 152s will have carb heat. The Citabria I was flying for tail wheel training has carb heat. So that effectively just melts that ice, and then what you'll see is you'll see the RPM increase if there was icing present. Yeah, and that's another point. When you apply carb heat, you're decreasing the air density because you're raising its temperature. So if you don't have ice, you'll pull carb heat and you'll see a reduction in RPM. So you won't see it actually get better after a while if there was ice present. So here's that ice, obviously disrupting the volume of stuff going through the carburetor. I like that, volume of stuff. So, so the ignition system, right? This is the thing that drives the explosion in the engines. So the spark plug ignites this fuel-air mixture inside the combustion chamber. And in aircraft, they have a dual ignition system. So they'll have what they call a left and a right side. And that just means there's 2 spark plugs per system. And there's also 2 sets of magnetos driving those spark plugs. So it's a redundancy, right? If you lose half of your spark plugs, you still have spark plugs, half of them. Hopefully not 2 in the same cylinder, but you and then you have the dual magnetos as well driving that. Yes, and the other thing is you get a more efficient burn having 2 igniting points inside the cylinder, so you're not going to be wasting as much fuel. Yes, so I mentioned earlier that the magneto system it depends on the engine driving them, not the electrical system. So this is how you can start an aircraft without actually having battery ignition. You can just hand prop it.
I think back to all those old movies where you just
Yep.
foot up
And run away quickly.
A lot of those guys only did this because they already lost.
Yeah, they already lost. Yeah, you could tell who was. Don said a lot of guys only had one arm. So. The spark, yeah. So the spark can occur without the electrical system, and then hand propping can start the engine, but an experienced pilot should be at the controls, not chop the guy in half. I mean, basically, they just don't want you running at full throttle as he's starting it, right? So getting that right balance where it's just gonna, catch it and go. Somebody who knows what they're doing should be there. Failure to turn off the magnetos, obviously, if they allow the engine to start without the starter, can allow the engine to start just by moving the prop. I mean, it's a no-brainer, but it's in here because it's in the test and it's separately identified that way. So another thing they talk about is a ground wire on the magneto too is simply, it's almost like not being able to turn the magneto off. So if there's a bad ground wire, like it's rusted out or something, or it's just disconnected, it could still start. So that's one thing they've mentioned in the test before. So here's just a very crude drawing of the ignition system with the magnetos and showing both sets of spark plugs on the system. So if you look in the yeah.
So do you have to turn off the magneto in order to start it by hand?
No, you would leave the magnetos on both and then you would hand prop it. So, but you wouldn't use the starter. So from the ignition system here, you would probably set it to both, and then I've never hand started it, and I hope you never have to. But yeah, the magnetos would need to be on. I'll give you a perfect example. One day, I was going flying, and I forgot to turn the magnetos on in my Saratoga, and it was cranking and cranking and cranking, and it never started. So in our plane, the magnetos are on actual separate switches. They're not part of this nifty little thing that the Cessna has, where you actually have to swing through the magnetos to actually hit the starter. So I actually have switches that are completely separate. Why isn't it starting? I didn't prime it. Yeah, whatever. Nope, magnetos aren't on. So good job. Yay me.
So you can't start the plane when the magnetos are off.
Yep. I found that out.
So they have to be on when the magnetos start.
Yeah, you have to have, and like I said, in the Cessna, you actually go through turning the magnetos on before you get to the ignition or the starter. So, but in some planes, there's switches, so you actually have to turn those switches on.
So it's kind of like turning the key in a car, where you have to pass certain cars.
It's sort of like turning the key in a car. You have to pass through. Well, there's an accessory stage in that, but in this specific case, it's magnetos. I don't know if cars have magnetos. Maybe somebody knows.
Race cars have them.
Do they? Okay. Race cars have magnetos, okay.
To a magneto is by their lawnmower.
Lawnmowers have magnetos.
Lawnmowers run off magnetos. They don't have batteries. They don't that.
Oh, that's when you crank. Yep, that's right. You crank, pull the
You
crank.
just
Yep.
pull, and as soon as the magnets.
Good
pass
point. I
through,
like
you
that.
gotta
I
stop.
don't remember that one. Yep.
Now on an airplane, instead of being hardwired always on like your lawnmower, an airplane has an off switch
Yeah.
and it's just a safety feature.
Yep.
There is no real on for a magneto, but there's an off. So when we say we're turning an airplane on, we're really taking it off of off.
Off. We're ungrounding the magneto, I guess, is
The off position
way to
is
say it, yeah.
disconnected. You connect the magneto by a circuit completed.
So why would you want to turn it off? I mean,
why would you want to turn off? So somebody doesn't hand prop it and bust their arm or head or something.
or
Yeah.
steals your airplane by and starting it.
Well, I mean, it's pretty easy to steal a plane. To be honest, have you seen the lock on an airplane door? It's like pathetic.
When
And
you want to go push the plane, you move the prop.
yeah, that's the other thing. Sometimes people will move the prop because like on any 2-3 blades, the prop could be positioned right in front of the nose wheel, and that's usually what you tow it by. So somebody's going to have to move the prop out of the way with their hand. So if that magneto's not turned off, yeah. So you definitely want to have it grounded or turned off at that point. Yep.
And just because the prop's off, I never touch the prop until I get an okay from her.
Yeah.
Yeah, it's worth it. It's always a good safety question every time.
Yep. Yep. So starter then is powered from the battery, right? And that's what's cranking the prompt. So it's acting like the guy out there cranking it and twisting it. Fouled spark plugs, I mentioned earlier. This is carbon buildup, and it can also, cracking can happen because of overheating on the spark plugs. But some other problems like shorted magnetos and poor timing are other sources of problems with the ignition system. So if things are running rough, you could have this carbon deposits on the spark plugs. One of the magnetos isn't running. One of the startup checks we do is we turn off the left and the right magneto system independently to make sure that they have an equal drop, or maybe one doesn't have. You would know one doesn't have any drop. That means it wasn't ever operating in the first place. But that's one of the checks during a run-up, is to make sure that both of those are functioning. So it's pre-ignition, not detonation, can occur with foul spark plugs. So there's the hot carbon deposit, the fuel-air mixture comes in, and it pre-ignites before it was meant to with the spark. And then I mentioned a broken or loose wire in the ignition system can allow the engine to start even if it's in the off position. We talked about that at length. In this case, you can reduce or cut the mixture and put the fuel selector in the off position. Basically, don't allow any fuel into the engine if it, for some reason, starts and you're like, oh, crap, how do I turn it off? But that would be the way to do it. Oil system is one of the things that helps cool the engine in addition to airflow over the engine. It's probably the most important. It keeps it running smoothly, of course. It lubricates the engine. It reduces the friction of the cylinders. It also provides a super tight, efficient seal between the walls of the cylinder and the piston. And then it additionally draws heat from the engine. So you could see the problems you would have if you had low oil pressure. Filter prevents contaminants from getting recirculated back into the engine. And where would these contaminants come from? Well, brand new engine, what they do is they score the inside of the cylinders and they let the piston work it in. So you run mineral oil, which is a higher viscosity oil, for a period of time when you're breaking an engine in. And that rough surface is really fine, but bits of metal and stuff are getting scraped off of that piston. And so the filter will catch some of that. And the rings on the pistons and the cylinder metals, there's some dissimilar metals. So what they'll do is you'll have your oil change actually analyzed by a lab and look at under a microscope and look at what, or even Marcy would know too. But they can analyze the oil and determine what metals are in it, and they'll send you a lab report back. So let's say your rings are wearing for some reason in your engine. The oil sample could actually tell you, hey, we're seeing a lot more chromium, or whatever metals. I I just look at the report and read it. So, but so having the oil analyzed is a good way to understand how healthy your engine is. So that filter is, I mean, everyone knows there's oil filters, but that's why they're there. Oil's monitored in the cabin through temperature and pressure probes that are connected. And temperature can be low and the pressure really high when you first start the airplane. It looks like something's wrong, but it's just that the viscosity of the oil is cooled. It's, you know, and especially in the winter, you'll really see that where it's like, wow, why is the pressure so high? Well, it's trying to push this really viscous oil through your system. So generally speaking, you should allow those things to normalize before you take off. So sometimes in the winter, you'll, you know, have a nice long taxi to get things warmed up. And you should even do that before you run the propeller during a startup check. You want to make sure that oil is really nice and smooth going through there, because it's also lubricating a constant speed propeller, the governor on that. Right, governor. All right. Slide 31 of 90 at 6:45. Okay. Overhead view of a horizontally opposed engine and the oil system. There's a sump point in the oil system, and the dipstick reaches down to that, so you'll be able to see how much oil is in your entire sump just by pulling the dipstick out. Pretty common thing. So usually the owner's manual will tell you how much oil is good operating range. Smaller planes will be 5, 6, 7, 8 quarts. Larger planes, 9 to 12 quarts. We run right around 8 in ours. If it's low, you definitely want to add oil, for sure. And again, the gauge here is typically this 2-in-1 thing showing both pressure and the oil temperature.
So you check the dipstick when it's warm too, just like a car? Or can it be accurate, or cooled for it to be accurate? Or?
It's, yeah, you know, that's a good question. I mean, I usually just check at the beginning of the day, so, but it is harder to check when it's hot. It's harder to see
Oil
when it's
change
hot,
change
yeah.
volume a lot with heat.
Yeah. Yeah, it seems pretty consistent even when it's
Over
hot.
the operating range, it doesn't change volume much.
Yeah. If your engine's,
Marcy's nodding yes. I think I'm on the same.
yeah, it doesn't really, yeah, it doesn't expand or contract a lot. It gets more viscous or harder to move. But yeah, I mean, if the engine's running really well, you'll have oil that's really hard to see. Like, you know, when everyone thinks oil is black, but that's usually about when you're going to change it, right? Yeah, but at a clean oil change, it's going to be hard to read that dipstick. So, oh, lab report, they're not bad. You buy kits, and they just send you like a little, it's like a urine sample jar that you put the oil in, and it has like a serial number on it, and then you send it back. So you can order kits like on Amazon even, or Sporty's Pilot Shop, and I think the kits are like $25 or $30. They're not bad. So when I go do my oil changes, the guys there they do it as part of the oil change. They'll send it out to the lab, and then like a week or so later, I'll get the report back. So the different kinds of fuel systems, there's basically two. I mean, there's a gravity feed, and then there's a fuel pump driven fuel system. Gravity feed, pretty obvious, high wings, right, above the engine, just gravity feeds it in. Usually those systems will feed both wings evenly, but you can select if you want to feed only from one or the other wing. And then a fuel pump system has an engine driven pump, which is good, right? Because if the electrical system goes, you want to still pump fuel. But there is an auxiliary electric pump one. Kevin, did you have a question?
I do. Why
Yeah?
would you want to select just drawing fuel from one wing? Because wouldn't that make that wing lighter?
Yeah, why would you want to draw fuel from only one wing? Well, if, you know, let's say for whatever reason one side isn't clearing out as fast as the other and you get off weight, you would intentionally switch to the other.
Okay,
If you're expecting both.
Okay.
Another reason you might only choose one tank is that, say you found contamination in that fuel tank, like water contamination or something.
But routinely, you wouldn't just draw fuel from one side tank.
You would leave it in both.
Right.
I mean, the only reason to leave it in left or right is if you saw a specific imbalance that you wanted to correct in flight. Yeah.
Those tanks are usually at the root of the wing, or they're not outboard too far, are they?
Auxiliary tanks can be at the tips. They have tip tanks, but generally speaking, because of the hedral of the wing, the fuel, rests near the root of the wing. Yeah. Filler caps are generally a third of the way down the wing. I think ours are closer to half, right? Yeah. But most of the time you'll see them about a third of the way down the wing. So gravity feed, right, usually feeds both at the same time. You can select left or right. A fuel pump system may feed both, but ours doesn't. There is a specific left and a right feed, so you have to manually switch it on the fuel pump system. The engine-driven pump will ensure that fuel is pumped even if you lose electricity. However, if that fails, there's an electric pump. It draws a lot of current, so if you generally use it during critical phases of flight in case the engine-driven fuel pump goes. So like if you're climbing out during takeoff, you'll run that auxiliary pump as well as the engine pump. There's a pre-flight check where you check it, the pump on and off and make sure everything's working correctly. But yeah, usually during takeoff, climbs, and your approach to landing. Priming is pretty common in most planes. Unless it's been run recently, and I'm saying within an hour, you'll typically have to prime it, and that just means introducing a little bit of fuel air mixture into the combustion chamber without the engine running and then starting it. Hand priming is common in some smaller planes. There'll be a little thing that looks like the carb heat knob you push in and out. You'll unlock it, pull it out, and it'll go, and then you push it in, and then you go, and you go like that about 4 or 5 times, and then that's priming it. You lock that knob, and then you do a startup technique. Priming technique it can be very aircraft specific. So usually there's a good technique documented in the checklist that if you just follow that and don't try to outsmart it, the plane will start on you. I've seen a lot of people get into trouble, and I've even done this. I think Ryan was with me in the Diamond, the DA40, and I was having a hell of a time getting it primed and started. And it wasn't funny for me anyhow. Maybe it was for Ryan, but yeah, so these techniques for priming and getting these planes started can be kind of quirky in some cases, especially when they're hot. They might want different things. So, maybe 1 shot of primer, maybe it needs 3. I don't know. How's it feeling? You got to talk to it. What do you want? But yeah, priming technique is kind of a funny thing. There doesn't seem like there's any magic wand for it. Fuel gauges you'll find in the flight deck always, but or only on the actually that's not true, not always. You can find them actually attached to the fuel tanks on the wings, either inside the plane or outside. Typically though, there's gauges inside the aircraft. I like it when there's gauges actually on the fuel tanks, and ours has gauges on the top of the fuel tanks. So mainly because you can't see how much fuel's in it just by opening the cap, because the fuel's all down at the root of the wing. But in a Cessna, you can actually take a fuel stick rod with graduated markings on it, and then see what how much fuel is in it directly, and that's the recommended thing on a pre-flight. So confirm what the gauges say with an actual inspection of the tank. Yep. Obviously, topping off the tank, you'll know they're full. So, yeah, this is that fuel selector, so it's important. The only reason to put it on off is if you have some sort of emergency situation that you're dealing with, fire maybe in the engine, and you want to cut off all the fuel going in there so the fire doesn't get worse and come back into the tanks. Yeah. I mean, storing the plane, maybe you'll turn it off, or when they're doing maintenance, they might turn it off.
Do you turn it off when yours is in the hangar?
No. I just worry I'd forget to turn it back on. Kevin asked if I turned it off in the hangar. I do not.
Well, leaving a motorcycle, we would trim it off. My gas is on the floor.
Oh, and that's not good.
Or trying to start the motorcycle when the fuel's off.
Turn the fuel on.
I've done
Trying-
it so many times.
Yeah, I mean, if you can't start the plane, start here, you know, and then go up the fuel system chain. Well, start at first and see if you actually have fuel in the tanks, then go here. Yeah. Well, yeah, and then in flight, if you do have a situation where you're not pulling from both left and right, I could see a situation where you have it on both. For some reason, it's not drawing from the full tank at all. And I get a little apprehensive, and I might say, you know what? I'm going to encourage it to draw from that tank, because I see 3 gallons in my right wing and, 50 gallons in my left wing. So, so there could be a situation. But definitely, if you're in a plane that doesn't have a both feed, this is like super critical. I don't know how many accidents happen because somebody forgot to switch. Oh, John Denver. Wasn't it him? Yeah, in Monterey. Yeah. Yeah.
What effects would you feel on the plane if there was a disproportional weight on either side?
What effects would you feel on the plane if it was off weighted because of fuel distribution, right? Yeah, you would be you'd probably be pushing on one of the rudder pedals more. You might be banking the plane weird. You're definitely not going to have straight and level coordinated controls. Yeah, so there. Turning the fuel on, well, yeah, it is a pre-flight. There's a set to both is what it says in the Cessna usually. So just confirm it's set to both, yeah. If you're going through checklists, you shouldn't miss it, right? But you have passengers in the plane, you never know what can happen. So, even after you pre-flight. I can think about that. Touchy, right? What's this do? Hey. Everyone's Pee Wee Herman, right? The passengers. Anyhow, so that fuel selectors. What's that?
It's not me. I was like this the whole time. Nothing.
Well, I was thinking of that kid in, was it Home Alone? The neighbor kid that came over and he got counted instead of, Macaulay Culkin. But he was like poking through the kid's stuff in his room and everything. What's this do? Anyhow, sorry. That's just the imagery that comes into mind. So the fuel selector is located on the floor typically. In the Cessna, it's like right there. Same thing in the Saratoga. It's like right on the floor in front of the trim. Now a sump anywhere is just a low point, right? So the sump and the low point in the fuel system and there's drains that we can actually collect samples of the fuel. So we can look and see if there's water present, if there's sediment. Sometimes the drain itself can get cruddy and that's what you're reading. So just flushing the drain sometimes clears out particles. Since water is heavier than fuel, it'll collect in the sump. Also, when you take a fuel sample from that drain, to see if there's water in it, you'll see that the water is sitting at the bottom of the sample cup and the blue fuel is floating on top of it. And you should continue to drain until you no longer see water. It could be a condition where one wing for some reason has water in it. You need to go somewhere, just run off the other tank on the other wing. So you put the fuel selector on that wing. Knowing you only have what's in that wing to fly, but I mean, that could be a case where if you know something's up with sediment or particles in one of the tanks. Contaminated fuel obviously will result in rough or a stopped engine. There's a danger in cold climates where that water can actually freeze somewhere in the fuel system and then prevent fuel from getting anywhere, and then your engine will stop, obviously. So it's really important to know that there's no water contamination in your fuel, especially. One tip is that you can top off the tanks. I like to do that when we get somewhere. I'll just have them top them off immediately unless I don't need them topped off for some reason, because that air in there can cool and condense, and the water vapor can come out and then actually get in your fuel if there's available space in there. So topping off the tanks leaves no chance for that water vapor to be in there. Here's a thing you might not think about, but filling tanks prior to inspecting the drain fuel is not a good practice. Can you imagine why that is?
Mixing the water out.
If it's already contaminated, you're just mixing it up. And you may not even see the contamination. Yep. So, so you really want, if the plane's been sitting, that's a chance for everything to settle down. That's the best time to take those drain samples. So if somebody's going to come over and fuel your plane, try to get those samples before they disturb the fuel tanks. General aviation planes use 100 low lead. It's blue-colored avgas. And for the most part, there's other grades, but I haven't seen other grades recently anywhere. Maybe out in the bush somewhere, they'll have 90 or 80 or something. They're color-coded. For us, most of the time, we're gonna see this blue stuff. And avgas is still leaded. They're trying to.
They let you fill your vehicle up at
People do it. I've seen some people shooting off to Lake Nacimiento, stopping at the airport, and
Not supposed to.
Will they let you?
Yes,
oh, nobody's gonna stop you. Let me put it that way.
Performance engine trade.
Yeah.
I know. Who's does self-serve?
Well, Ryan said, how long does avgas last? So if you have a 50-gallon tank and you burn 10 gallons an hour, 5 hours. That's not what you were asking. I'm not sure. I mean, how long can it sit in the plane without using it? Yeah, that's a good question. Yeah, I know. Why aren't you flying your plane? I mean, I don't know winterization practices because we don't have to do that here. But I know there are some things that people do with winterization. Yeah.
Well, I know with cars you can recycle your used oil.
You can recycle the used oil, yeah. But yeah, I don't know even if they do that. They might do that, but they won't throw it back in a plane unless it gets processed. So yeah.
Pilot's not stable.
Ryan asked how long is
Yeah, that's what I gave a really crappy answer to that question. So sorry. I don't know.
It probably lasts a lot better than automobile fuel now because it's not all juiced up with environmental.
It's leaded, yeah. I mean, it's
It's not oxygenated and all the other things
Yeah.
you do to automobile fuel
Yeah.
will ruin it.
Although, I mean, you get
Water,
back to the
turbo
point,
water.
if I'm relying on that fuel to keep me in the air, I'm probably gonna put fresh fuel in it. If it's-
well, yeah. If you haven't flown it for 9 months, well, I think 9 months is okay. But if you're looking at your plane's been sitting in a hangar for 2 years, it's going to have to get an annual anyhow. I mean, after a year, it's going to have to get an annual, and during the annual, they might go, your fuel smells funny. I mean, maybe it smells funny after a while. Yeah. So, yeah. Diesel is a fuel option they're looking into. Some planes will actually run on it, but it's not really taking off, pun intended. Jet A is a form of kerosene. It will not work in your airplane. Your airplane will not go faster if you put Jet A in your 100 low lead plane, so don't do it. It will smell different from avgas. It's colorless. Nothing prevents a guy who's filling your fuel for you on the airport putting Jet A in it, though, so keep an eye out. Detonation can occur using lower grades of fuel. So the mixture explodes instead of burning evenly. This causes the engine to overheat. Talk about some of those techniques in a later slide. When fueling a plane, it's important to ground the aircraft with metal-y things, not plasticky things. Metal-y things. Because I heard tale of somebody who had emptied a wing into a plastic bucket and then burned the entire plane down. So, metal things connected to the fuel source, connected to your plane. They're both grounded to the same thing. The nozzle grounded together. Hold the nozzle against some metal part of the filler cap while you're filling it. Don't explode your plane. The electrical system, typically a 14 or 28 volt DC system, and it'll power, the communication radios, avionics, of course the lights, and all those pumps that we talked about, the auxiliary and boost pumps that are not engine driven. The battery is recharged from an alternator, pretty similar to a car, right? And that's attached to the engine shaft. There's some planes you can actually see the little belt right in the front of the plane as you're inspecting the aircraft, you'll see the belt attached to the shaft that's going to the alternator. And a typical pre-flight check is to just make sure that's snug and on there. The alternator supplies slightly higher voltage in order to charge the battery. So that means if it fails, then your battery will eventually drain. Or if it's unable to charge above it, even if it's just charging a little bit under, your battery can drain. It just takes longer. An alternator overcharge could occur. And if that happens, you might want to turn it off because it's driving way too much voltage into your battery. It could blow up your battery and cause a fire in your airplane. And then you have to make an emergency landing usually. So don't, the best thing to do is just, there's usually a separate switch for the alternator. You can just pop it off in that case.
Again, back to what you said before, don't explode your airplane.
Don't explode the airplane, keys. But this is one technique you can use and apply practically to not exploding your airplane. So, alternators, so this is a written question. Alternators provide more power at low RPMs than generators. That's what's special about them. An ammeter will be in the flight deck. It'll indicate if the battery is being charged, and sometimes it might just be a little light bulb that pops on. In planes, there are just indicator bulbs. Sometimes they call them dummy bulbs. But usually there's a press to test button in the plane to make sure that the dummy bulb is actually getting power and it works. So yeah, the light's great, but if you don't know if the light itself is working, how do you know if it's going to indicate correctly? So you do the press to test switch, and then that lights all of the lights in the cabin. You can verify that all of them are actually getting electricity. You don't have to encourage a failure situation to check the light. The ammeter will center at 0 when there's no current flowing in either direction. So plus sides indicate that the battery is charging. That's what you want, a little bit on the plus side. A minus charge if it's draining. A full scale deflection minus means that the alternator is not doing anything. You're completely running off of the battery. So here's what an ammeter looks like. There's also a load meter. A load meter is useful if you are in a situation where you've had a failure of your alternator. And you're relying only on your battery, and you need to reduce the load, because if you reduce the load on the battery, you'll get longer life out of the battery. So in some cases, critical things only stay on: comms, the pump for your landing gear, if you have retractable landing gear. You can basically evaluate what you need and what you don't need based on the situation of flight and eliminate load to extend the life of the battery. Newer aircraft will have circuit breakers, and the pull type. So this is one way you can reduce the load, is you can pull out certain things that you're not using at that time. Avionics usually on a separate bus. So if you just want to drop the avionics altogether because you're in that situation and only use the battery for putting the gear down or other things important to finishing that flight in an emergency situation, then you can do that. Also, usually the avionics draw a lot of power, so during a startup, you're not going to want to have it on. You want to give all that power to the starter to turn the engine. And I mentioned electrical system operates a retractable gear through hydraulic pumps. But you can retract the gear. They'll free fall if you do lose power. So there's an emergency override. And what you can do is basically decouple the pump from the hydraulic system. You pull the breaker, and then there's a lever you pull, which will allow the gear to free fall. Sometimes you got to shake the plane a little bit to get them to lock, because there's sort of like a locking joint on the gear. Definitely want to know that they're locked before you try to land in that situation. If you do have electrical, the gear down lights will indicate. So at least you have a good sense of things are locked in. Hydraulic fluid operates brakes and the retractable gear. For the most part, that's it for hydraulic fluid. So another section in the written is about engine temperature management. This is what to do if your engine is overheating. So low oil can result in engine overheating or seizing. So looking at that oil temperature and pressure gauge is a good indication or a heads up that this may happen. Another way to know this is there's cylinder head temperature probes on the cylinders, and also an exhaust gas temperature gauge, or either. You can look at those to get a sense of how hot the engine's running.
Question.
Yeah. Oh. Is there a standard for how long the battery should last in an emergency situation? No, there is no standard. Yeah, there isn't. It's really going to depend on how much of a load you're drawing off of the battery. So your best bet is just to, I mean, and there's some more advanced airplanes will, yeah, well, you don't have to get on the ground if you lose power. People flew planes. The Bright brothers flew a plane without any batteries in it.
That's what the magnetos are.
Yeah. That's what the magnetos are for. Yeah, there really isn't any sort of thing that says you have to have so much time. We're having some avionics installed right now in our plane that have a 30-minute backup battery, which, given that we're taking the vacuum system out, I mean, we'll talk about that later, you want to have something like that, because the vacuum system runs off the engine, will power a lot of instruments even without electrical power. Not in this section, but we'll talk about that in the next section. So, pulling the vacuum system out, not having an attitude indicator that can run when the power's out, you want battery backup in that case. So, but nothing says you have to have it. We just chose to do that. Too lean of a mixture can increase engine temperatures, obviously beyond acceptable operating limits. Again, that's a test pilot thing. What are acceptable operating limits? You'll find out quickly if you've exceeded them. Steep climb can reduce the airflow in the engine, so that's another thing that can cause overheating. So if it's a really hot day, this is a typical scenario. It's a really hot day, the engine's not performing, the air density's low, you're trying to climb this bugger out, and there's just no cool air flowing over it. So that can really increase the temperature. So what you have to do is you just have to lower you can't climb that. You have to lower your climb rate and get more airflow, or burn more fuel by throwing a richer mixture into the engine. That can reduce the temperature. Lower grade of fuel can also increase engine temperature because of that detonation we talked about. Engine can normally be cooled by written test stuff here. Reducing the climb grade rate, increasing the airspeed. That's the other cooling element you have, right, is the air flowing through the cowling. Reducing the throttle, obviously not throwing as much power at it, or enriching the mixture. I mentioned the engine temperature is monitored by that exhaust gas temperature, or the cylinder head temperature, a CHT probe. Typical plane will have just one probe, one or the other, but there's some planes that will have cylinder head probes for every cylinder, so you can see if one in particular is running hot. You don't want to burn that one out, so you kind of balance how much mixture and fuel flow to keep the engine running optimally based on that one hot cylinder. Yeah, so these just basically give you feedback, indicate if there's any problems or unexpected changes in engine operation. In our plane, we really have to keep an eye on cylinder head temperatures, or I just burn a ton of fuel. But I'd rather not burn a ton of fuel. I'd rather just watch the engine gauges and burn a reasonable amount of fuel. Yeah, so it can help determine if leaning or enriching may be needed to improve fuel performance, keep the engines cool. Some of the additional topics, and this is perfect, we're right at time for the break. Turbocharging. Our plane is a turbocharger. It takes the exhaust gas and compresses the air, so it increases the air density going into the engine, which allows us to go to higher altitudes. Yay! So our engine doesn't suffocate at 10,000 feet. We can take it up to 20,000 feet. Turbines, fascinating topic. They're just really cool, but a very long topic. But the basic idea of a four-stroke engine still exists here. There's a intake, compression, combustion, and an exhaust phase on these engines. It's just the way that they do it and how compressed they can get that air really allows them to generate a lot of thrust. There's two types of turboprops I saw in the book, and the main difference is one of them actually intakes air from the back, So it faces the other way. And one of them intakes air from the front. But you'll usually be able to tell a turboprop because it has these big pipes coming out of the front of the exhaust. So the ones that are reverse mounted, those pipes are really far forward. It's pretty obvious. Brian would know because he's all about turboprops and jets. But yeah, so a turboprop will run a propeller blade just like a reciprocating engine type one, whereas a turbojet is running the exhaust gas and using thrust and pulling the plane forward that way. There was a little bit about oxygen systems and oximeters. The thing that we'll need to know about oxygen for the written is that above 12,500 feet, you need to start using oxygen. It's actually a federal regulation. The pilot, after 30 minutes, needs to use it. If he comes up to 14,000 feet, you've got to use it immediately. And if you're above 15,000 feet, everyone in the plane has to be offered oxygen. They don't have to use it, but the pilot or anyone who's a critical crew member has to be on oxygen. Pressurization. In this case, you don't need oxygen. You're pressurizing the air, so the amount of oxygen in the air is the same because you're pressurizing it. So you don't need an oxygen system, and it's very comfortable because you're just So, but that's why in the airplane, when the pressure system goes, the masks come down to give you enough oxygen so you know what the heck you're doing in emergency.
When it pops down, it's an offer.
It's an offer. It is an offer. You don't have to do it. So. Anti-icing and de-icing systems. The most common one of these things called little boots. They're little rubber tubes that run on the front, and it's like a rubber covering with little air tubes in it. And what you'll do is you press the button in the cockpit, and the tube inflates, and it breaks apart the ice. Is the idea. Obviously, if the icing has gotten so bad, the boots won't do anything for you. Large jets have an hot air tube. I think they take exhaust gas and just run it through the leading edge of the wing. So you'll see like a stainless steel sort of leading edge of the wing, and that's usually a de-icing system or anti-icing, de-icing. And anti-icing is before icing, and that's like spraying glycol or keeping the plane in a hangar on a cold, snowy night is a form of anti-icing, honestly. But those, I don't know if you guys bothered reading those sections, but as far as I know, the only thing you're going to probably have to know is that thing about oxygen as far as the written goes. So quickly, so we can go to break. Reciprocating engines, engine temperature management, carburetor, heat, carb icing, mixture, and why mixture is important, adjusting it for altitude. Knowing what the magnetos are for in the ignition system. Understanding detonation, pre-ignition, contamination. They will have questions on constant speed propeller. They never used to when I took it, but now there's more training planes that have constant speed propellers. Throttle controls manifold pressure. Prop sets the RPM. It's more efficient and more flexible depending on the flight conditions. That's why they have them. A little section on ground operations, aviation, fuel practices, knowing what the sump and straining and understanding grades of fuel, different types of fuel. This thing about filling the tank to prevent water vapor from condensing into your fuel. There's something about hand cranking, checking oil pressure when you start up, making sure that things are operating. One thing they had specifically is during startup not to leave the engine full bore, like pull it back to whatever the recommended setting is during idle operation. Another one is these cold weather crankcase vapor lines getting iced is a question on it, and why you would want to keep warm the engine compartment in cold weather situation. That question appears on every test. I don't know why it's there. I've never actually run into this in a practical situation. So, but you know, we don't live out in the winter, so. Enough pilots in Alaska maybe that this is a reason it's on the test, so. And high altitude. Electrical systems voltage, the voltage of the systems, the 1428, and then what the ammeter does. Why is an alternator better than a generator? And then just knowing that a failure electrical system results in a loss of the avionics. So, all right. Break time. Thank you. Thank you.
Great ground run.
Phyllis 1455, tower 33.9. Station 17